Okay. Yeah. Do you have any questions either about the final or the recent midterm or the combinatoric stuff or relations, I suppose? I have no idea where people are in general, but
Yeah, so I guess about the final, the question is whether it's going to be the same structure as this past midterm.
yes. So I'm going to write a slightly longer exam, not a much longer exam. I'm not trying to write a 3-hour exam. And what I will do is have a 24-hour window starting on our usual time on Friday to take the exam. And so if people are at different time zones, then they'll take the exam at some point during those 24 hours. They'll have 3 hours to take the final and then submit it to me. Yeah.
And so are you planning on putting, I guess, making it cumulative, putting stuff from all sections, or how should we
Yeah.
prepare?
Yeah, it's going to be a cumulative exam. So I would definitely recommend going over like old midterms and checking on some of that older stuff from chapter 1, chapter 2, logic, functions, sets, um, and then a lot of the newer stuff that we've been going through. So yeah, it will be cumulative.
Okay, and with the last midterm, when are we going to get grades back on that?
You should have them back by tomorrow. I've essentially graded all of them except for 1 or 2. And it's just a question of me going through, checking the grades and submitting them, but they're graded more or less. So.
Okay.
Mm-hmm.
With that exam, I definitely have a question
Okay. Yeah.
about 3 and 4.
Yeah. Definitely. So, um, let's see. Let's start with problem 3. Mehmet, is it all right if we go through? I'm not sure if you have already seen me go through these, but it's fine. So problem 3 on the midterm, if I recall, was show if, well, yeah. So let Q1 through QK be primes. Show that if 3Q1 times QK minus 1 is composite, then one of its prime factors is of the form 3K plus 2. Right? This is essentially what the question was.
Yeah, I think that's what the question was. I don't have it right in front of me.
That's fine. This might be a slight restatement, but this is what the question was asking. Okay, so as mentioned in the hint, the thing that you want to do is you want to examine this number that I gave you modulo 3. So let's do that. On one hand, if I just take some number, 3Q1 all multiplied all the way through QK minus 1, and I look modulo 3, what answer will I get?
It'll be 2, right?
Exactly. You can immediately know that if you have 3 multiplying anything, that'll go to 0 modulo 3. So this will be -1 modulo 3, which is the same thing as, it's congruent to 2 modulo 3. So sure, we can write it as 2 mod 3. If we want to write it in terms of congruence, right? Okay. So now let's assume, for the sake of contradiction, that, well, if I'm assuming that 3q1 times all the way through qk minus 1 is composite, then I know that I can write this as some product of primes, right? I can write down the prime factorization. So I can write 3q1 times qk minus 1 is equal to, and I'll write p1 to the a1 all the way up to pl to the al, right? I'm just writing out the prime factorization. Assume for the sake of contradiction that all prime factors, if I want to contradict that some prime factor is of the form 3k plus 2, then what must all the prime factors look like?
Wait, what did you do there with the 3k or qk minus 1 equals? Yeah,
So
right there.
so 3q1 all the way up to qk minus 1 is some number, right?
Yeah.
And it has some prime decomposition by the fundamental theorem of arithmetic. In other words, I can write it as a product of primes.
Yes.
And so I'm just saying I'm going to give names to these primes. P1 is the name of one of the primes that divides this number. And maybe, you know, P1 to the A1 divides this number, for instance, right? Like I can have 3 times 3 times 3 dividing this number, perhaps.
Okay.
So this is just the prime decomposition of this number.
Okay.
Okay, so I want to show that one of these primes, my board work is messy, but I have a small board, so forgive me. So I want to show that some pi is equal to 3k plus 2 for some k. If I want to contradict this, if I'm going for a contradiction, how do I contradict one of the pi's being of the form 3k plus 2? Or in other words, one of the primes being congruent to 2 modulo 3?
Showing that it's somehow other than modulo 2, like, or modulo 3 equals 2 would be some modulo 3 equals 1 or 0.
Exactly. The only possibilities for a number to be congruent to modulo 3 are either 0, 1, or 2. I want to show that one of them is congruent to 2 modulo 3. So if I want to use contradiction, I'm going to assume that all of the primes are either congruent to 0 modulo 3 or congruent to 1 modulo 3. Okay?
Okay.
So in other words, by this assumption, P1 is equal to 3K1 plus, I'll call it I1. I don't want to get too messy with the indices here, times all the way up to 3KL plus IL to the AL. But essentially, I'm just saying all of these primes can be written as 3 times an integer plus a remainder where the Li, or the, oh shoot, I've messed this up, IL. I said L, where all the remainders are 0 or 1, right? All that I'm writing here is that all these primes are congruent either to 0 or congruent to 1 modulo 3. Is that okay so far?
Yeah, I'm just trying to write it all down.
Yeah, sure.
So you're saying that to contradict what you're saying, what the PI is 3k plus 2,
Right.
then
I want
all
to
of them have to be 0 or 1.
exactly all of the. If I'm going for a contradiction, I'm going to assume that all of the remainders are either 0 or 1.
Okay.
Okay. But now, by the hint, I want to examine this product of primes modulo 3. And the hint that I essentially wrote is that the mod 3 operation essentially distributes. So if I want to compute this whole thing modulo 3, it's the same thing as computing this thing modulo 3 times A1 copies of this thing modulo 3 times all these, and then I'm going to compute this modulo 3 AL times. So in other words, when I compute this big product of things, 3k1 plus I1 A1, when I compute this whole product modulo 3, that's the same thing as just picking off the remainders. I'm going to get I1 to the A1 times IL to the AL mod 3. This was also part of the hint that I wrote, which is that mod kind of distributes through products. So this number is a product of a bunch of numbers which are either zeros or ones. What could such a product possibly be?
So the product's going to be 0.
This is equal to either 0 or 1. Right? If one of the primes is actually 3, the only prime which is 0 congruent to 3, then it'll be 0. If none of the primes are congruent to 3, then they're all going to be congruent to 1 modulo 3. And then I'm just going to have a big product of 1s. But the only two numbers that I can get when I do this computation are either 0 or 1, but never 2.
Okay.
So when I compute what this number is modulo 3, looking at it this way, I get 2. But then if I assume that all the primes are of the form 3k or 3k plus 1, and then I compute modulo 3 in the product fashion, I get that it's either 0 or 1 modulo 3, which is a contradiction. You can't have the number be both congruent to 2 and congruent to either 0 or 1. Any questions on this?
I'm a little confused as how that gets to the conclusion. Like, what even is the conclusion?
So what I'm trying to show, so yeah, we can kind of trace through this whole argument. It's not structured very well on the board. What I'm trying to show is that if this number, 3q1 through qk minus 1, is composite, then one of its prime factors is congruent to 2 modulo 3. Now what I'm going to do is I'm going to assume, for the sake of contradiction, that all of its prime factors are congruent either to 0 or to 1 modulo 3, because that would contradict one of them being 2 modulo 3. Now I compute what this number is modulo 3 in two different ways. One, I just look at this expression and I see that it's congruent to 2. But if all the prime factors are congruent either to 0 or to 1, then when I compute mod 3 of this big product, I get either 0 or 1. A number can't be congruent to 2 mod 3 and also congruent to 0 or 1 mod 3. So I've reached a contradiction when I assumed that all of the prime factors were of the form 0 mod 3 or 1 mod 3. So one of them must be of the form 2 mod 3 or 3k plus 2 for some k.
Okay, that's a little clearer now.
Like maybe something that is useful to go through is, let's just do some examples. All right, I'm gonna pick some prime factorizations. Okay, so let's look at 7 squared times 13 mod 3. Okay, what the little hint says, that computing this modulo 3 is the same as computing 7 mod 3 times 7 mod 3 times 13 mod 3. All of this modulo 3. Okay. Well, what is 7 mod 3?
It'd be 1.
Yep. What's 7 mod 3?
It's 1 again.
Also 1. What's 13 mod 3?
Also 1.
Also 1. So 7 squared times 13 is congruent to 1 modulo 3. Okay. What about 3 cubed times, what's another prime? Times 19? Yeah, times 19. Let's compute this modulo 3. Well, once again, this is going to be the same as 3 mod 3 times 3 mod 3 times 3 mod 3 times 19 mod 3. All of this mod 3. What's 3 mod 3?
0.
Right, so this is 0 times 0 times 0 times, what's 13 mod 3? Well, 3 divides 18, and 19 is 1 up from 18, so times 1. So this whole thing is congruent to 0 mod 3.
Okay.
So what I'm kind of showing here is that if I take prime factorizations where all the primes are either congruent to 1 mod 3, right? These two are congruent to 1, and 3 is congruent to 0 mod 3. Then when I compute what the product is congruent to modulo 3, it's always going to be either 0 or 1, because I'm always just multiplying together a bunch of terms which are either 0 or 1.
Okay.
And so the point that we're getting at is that if I have a number which has this prime factorization where all of the primes involved are congruent either to 0 or 1 mod 3, these numbers are never equal to 3k plus 2. Never. Because we compute modulo 3, these are always either 0 or 1. But this is 2 modulo 3. Let's do some other examples of some numbers that are 2 modulo 3. For instance, what's a good number that is 2 modulo 3 that's not a prime? Let's do 24. No, let's do something bigger than 24. Let's look at 32. No, 32 is bad. Let's look at 38, maybe. I mean, all these examples would work. They're just not so useful. So 38 is congruent to 2 modulo 3 because it's equal to 3 times 13, right? Plus 2. 3 times 13, wait. No, 12.
12.
Right? 3 times 12 plus 2. The prime factorization of 38 is 2 times 19. Right? And the point is, at least one of these has to be congruent to 2 modulo 3. And 2 is what is going to be congruent to 2 modulo 3. 2 is equal to 0, 3 times 0 plus 2. And then 19 is going to be 3 times 6 plus 1. So that when I compute modulo 3, I have a 2 times 1. So 38 is congruent to 2 mod 3. If this thing is going to be congruent to 2 mod 3, then this thing is going to be congruent to 2 mod 3, which means when I distribute the mod through, one of the factors has to have a 2. There's no other way to multiply a bunch of numbers which are either zeros and ones and get 2.
Okay.
Any other questions on problem 3? I realize that problem 3 is probably, well, it was definitely the hardest problem on the exam, and it was probably a little challenging, so I'm aware of that. But if you have any other questions on how the math works and how we're using how we're using modular arithmetic, please ask. So any other questions on problem 3 before I go on to problem 4? I'm gonna go put some water on. I'll be right back. Okay, so should I go on to problem 4?
Yes, that's okay with me.
Okay. One last remark about problem 3 is if you're trying to understand, if you're trying to look for similar problems which use the same idea of modular arithmetic, you should check that a sum of squares must be congruent to 1 mod 4 and never 3. I think this is a problem that I gave. Let me check if this is actually the problem. So let me find it. Is chapter 4 the? Yeah. Okay. Let me find the exact problem. Maybe it'd be good if I just did this problem again, actually, just because it's a good one. Where is the
I
sum
think
of?
I remember that on the homework or something.
Yeah. Yeah. It was on the homework, right? It's yeah, right. So it's saying that a positive integer of the form 4k plus 3 is never a sum of squares. So why don't I just go over this one again so that you have another example of using modular arithmetic in this way of deriving contradictions. So show that 4k plus 3 is never a sum of squares. So if I have a number that's 4k plus 3, it will not be equal to any n squared plus m squared, ever. Okay? So the way we prove this is first we examine what are the possibilities of n squared modulo 4. So to prove this, examine the possibilities for n squared modulo 4. Well, there are two cases. Case 1, n is even. If n is even, then n is equal to 2l. And so n squared modulo 4, or n squared is equal to 4l squared, and 4l squared is congruent to what modulo 4?
Sorry, 0.
Yep, 4l squared has to be congruent to 0 modulo 4, right? It's divisible by 4. That's the same thing as being congruent to 0 modulo 4. It's divided perfectly by 4. So if you're an even number and you get squared, you're always going to be congruent to 0 modulo 4. And that's very reasonable because when you square it, you pick up a factor of 4, right? If you're even, you're already a multiple of 2. When you square that, you're going to be a multiple of 4. The second case is n is odd. Then n is equal to 2, I don't know, b plus 1. And then n squared is equal to 2b plus 1 quantity squared, which is equal to 4b squared plus 4b plus 1. What is 4b squared plus 4b plus 1 congruent to modulo 4?
Just 1.
It's just 1, right? 4b squared is congruent to 0, so I get a 0 here, I get a 0 here, and I just get a 1 here. So what this says is any number squared, or any integer, when you take the square, it will always be congruent to 0 or congruent to 1 modulo 4. No square is ever congruent to 2 or congruent to 3 modulo 4. Okay? Is that okay so far?
Yes.
Okay, great. So now we come back to our original problem. Assume for contradiction that 4k plus 3 is equal to n squared plus m squared for some integers m, n, and k, right? Then examine this modulo 4. We examine both sides, mod 4. What is the left-hand side modulo 4?
Three.
Exactly. The left-hand side is congruent to 3 modulo 4. Then there are 4 possibilities here. I either have n squared congruent to 0 and m squared congruent to 0 mod 4, or I have n squared congruent to 1 and m squared congruent to 0 modulo 4, or I have n squared congruent to 0 modulo 4 and m squared congruent to 1 modulo 4, or I have n squared congruent to 1 modulo 4 and m squared is congruent to 1 modulo 4. Right? Squares are always congruent to either 0 or 1, so there are 4 cases.
Okay.
But what is 0 plus 0 modulo 4?
0.
What's 1 plus 0?
1.
0 plus 1 is 1, and 1 plus 1 is 2. So this side, mod 4, is only ever 0, 1, or 2. Whereas this side is 3. This cannot happen. This is a contradiction. If these two are equal, I can't have this thing be congruent to 3 and this thing be congruent to not 3 modulo 4.
Okay, that makes sense.
So do you see how this is the same logic or the same use of mod that we used on the exam? I mean, okay, I understand that the problem on the exam was harder and more challenging, and you haven't gotten enough practice on this. So I'm aware of that, and I take some responsibility for that. But I'm just trying to ensure that now you're kind of comfortable with seeing several different iterations of using modular arithmetic in this way.
Yeah, I mean, I definitely understand this, and I understood it on the homework, but I guess it didn't connect on the exam that it was the same logic.
Yeah, I didn't give enough practice problems on this particular use, so that's partially on me.
I don't know if this was mentioned, but do we have a date for the final exam?
Yeah, the date for the final exam is going to be the day that it was supposed to be, namely Friday, May 1st. But I'm going to give I'll do the 24 hours thing once again, where
Okay.
I'll give you 24 hours within that time you should take the 3-hour exam, or you should take 3 hours to do the exam. So yeah, I'll send out more details on that probably tomorrow or the day after.
Okay. And so like midterm grades are gonna come back tomorrow, but
Yeah.
is there gonna be any like read grade or corrections or
So
anything like that?
the grades
Or
on this
retest?
exam, so I don't think so. The grades on this exam were definitely better, and I think that they're going to be closer to reasonable distribution. So we'll see. That's still
Okay.
not totally taken care of. And another thing to note is that just overall, the grades in this class have been lower than one would anticipate for a standard distribution. So I'm not just going to give you whatever grade your points sum up to.
Okay.
So at the end there will be some amount of me working with the grading system. And so yeah, I don't want to say too much about it, but
Yeah, no problem. Thanks.
Before the exam, will we have all of our homeworks and everything graded? Because right now I just don't really know in terms of like where I stand in this class because I don't have like all the grades in one
yeah.
place.
So I will ask the grader to finish the homework grading, and I will give you back your midterm grades by tomorrow. So that should at least help, hopefully. And then I will definitely ask that the grader gets back the homework that you turn in on Thursday back before you take the final.
Thank you.
Mhm. And once again, you shouldn't just take your raw score and compare it to the standard A, B, C scale and say, this is where I stand in this class.
I have a question about the recent material.
Sure. Okay. So I also want to get to problem 4 at some point, but maybe we
Okay.
can kind of go back and forth. So I'm happy to talk about the recent material. Madeline, is it all right if I work on problem 4 from the midterm after a little bit of the new material?
Yeah, that's okay.
Okay. This was just more of like I guess like a clarification thing. So one of the
Sure.
examples was the password one.
Okay, yeah.
This is for permutations.
Yep.
And it was password, or you're supposed to find the total number of passwords. It could be 6, 7, or 8 characters.
Uh-huh.
And each character, I guess, could either be a uppercase letter or a digit,
Hmm.
but you were supposed to have at least one digit.
Right.
And then the way you did it, which makes sense, was you took like the total number of passwords possible, and then you just minus the ones that only had letters.
Right.
Uh, I kind of had a different approach. I said, so there's 6 possible slots.
So we're starting with the 6 length 6 passwords, right?
Yeah, because I mean it's applicable for the rest for the most part. So
Right. Yeah. You're just going to
solve that
sum
one
over the
easiest.
different cases. Yeah.
Yeah. But if there's 6 possible slots, then and one of them is only going to contain a digit, then I'd assume that for every single slot you have 36 available choices, except for one of the slots which would have 10. And then the total number would be 36 to the power of 5 times 10.
So I don't think that you're going to get the right answer when you do that, because, for instance, consider this password. Let's consider the password 111111. Not a recommended password. I think that in your scheme, you're going to overcount here, because you're going to count once where you put a 1 here, and then you have 36 choices, and then 36 choices, and then 36 choices, and then 36 choices, right? 1, 2, 3, 4, 5, 36 choices. But one of these choices that you're going to pick, if you have a 1 and then you have 36 choices, one of the options here is 1, 1, 1, 1, 1, 1. But if you just add, then you're going to have another scheme where you put a 1 here, and then you have 36 choices, and then you have 36 choices for all these. And for one of these, you're also going to be able to put 1, 1, 1, 1, 1. And so in this way of counting, it seems to me that you'd count this password several times. And in fact, you'd count this password like 6 times. Because
you
there
would
are,
change the position of the required digit.
right. Here you're requiring that this one is the 1, and you're letting these be whatever, but you're gonna reach the same password in kind of 2 different ways. And you could reach the same password in a lot of different ways if several of the different slots are digits, right?
Okay, I see.
Yeah, so I think that you'll be overcounting if you use this
Yeah,
scheme.
because I was thinking like if you multiply 10, then it doesn't really matter where you put it or like where that slot is technically, since it's just a product of it. But yeah, I could see why that would change it up. Yeah, that's all I had for that question.
Okay, that's a good question. Yeah. Any other more combinatorics-y questions? Have y'all seen the Pigeonhole Principle lectures? Those are probably supposed to be done, right? Today, maybe?
I was just wondering if we can do some more practice on like the combinatorics.
Oh yeah, I'd be happy to. Like you just want me to pick out some problems and do them?
Yeah, like some that are similar to like the homework probably.
Yeah, I'd be happy to do that. Before I do that, why don't you let me go over problem 4 from the exam really quick?
Yeah.
And then I'm happy to do some combinatorics.
Yeah.
Okay, so problem 4 on the exam was show there are infinitely many primes of the form 3k plus 2 for some k. Or in other words, there are infinitely many primes that are congruent to 2 modulo 3, right? And then the proof strategy is proof by contradiction. assume, well, what's the contradiction of there being infinitely many primes of this form? The statement would be there are only finitely many primes of this form. Assume there are finitely many such primes. And let's give them names, Q1 all the way up through Qk. So these are all of the primes that are congruent to 2 modulo 3. And then, according to the hint, you should examine this number, 3Q1 times Qk minus 1. Following so far?
Yes.
There are 2 cases. Case 1, 3Q1 times Qk minus 1 is prime. Is this of the correct form?
Of the correct form, in what sense?
Is it 2 modulo 3?
Yes.
It is. Could it possibly be on this list?
Could it be on like the, wait, what list do you mean?
Is it possible for 3Q1 times Qk minus 1 to be equal to one of the Qi?
I don't know.
The answer is no for several reasons. One is that it's too big. Because 3 times one of these primes minus 1 is going to be bigger than that prime, and then you're also multiplying by other stuff. Another thing is that if this whole thing was equal to one of the Qi, then we'd have Qi dividing itself. So Qi would divide 3Q1 times Qk minus 1. But if Qi divides the whole thing and Qi divides this thing, then that would mean Qi would divide -1, but no primes divide -1. No primes divide 1.
Okay, I see.
So if this is prime, then we have produced a new prime, which is 3 times Q1 times Qk minus 1 plus 2, right? This is just a way of rewriting this thing just so that it looks exactly of this form. A new prime of this shape. Right? So if it's prime, it's of the right form and it's not on the list. So this finite list of all of the primes of this form wasn't actually the full list, which is a contradiction.
Okay.
It's the same idea as in the regular proof that there are infinitely many primes. You multiply all the primes together and you add 1 and you say, well, if this is prime, it's not on the list, so I've made a new prime. Contradiction.
Yeah.
Right. And it's important to note that this is 2 modulo 3. So case 2 is that 3Q1 times Qk minus 1 is composite. Okay. What can we do now? Yep, we look at the prime factorization of this number, and then we use problem 3. Right? By problem 3, there's some pi, which is equal to 3k plus 2, such that pi divides 3q1 times qk minus 1. Problem 3 says, if a number of this shape is composite, then it has a prime factor that's 2 modulo 3. So I find that prime, which is 2 modulo 3, and I know that it divides this number because it's a prime factor. Is it possible for this pi to be one of the qi's? Or I shouldn't write p, just p. Let me just take p. Is this p one of these qi's?
I'm assuming no.
No, because if pi was equal to one of the qi's, then once again, pi would divide this whole thing, and it would also divide this, which means that it would divide this. Right? If you divide a sum and you divide one of the pieces of the sum, you have to also divide the other piece of the sum.
Makes sense.
So p is not equal to qi for any I. Thus, I have once again produced a new prime of the form 3k plus 2 for some k, which is not on this list q1 through qk. So anytime that I assume that I have a finite list, I can always find a new prime of the right form, not on the list. Either this is prime and then it satisfies the conditions that I need it to satisfy, or it's composite and one of its factors satisfies this property of being 2 modulo 3 and not being one of the QIs.
Okay.
It's a really cool theorem. And actually, there's a generalization of this theorem due to Dirichlet in the late 1800s. So we're getting to kind of modern mathematics. Which essentially says, if I'm not mistaken, that if m and n are relatively prime, then there are infinitely many primes of the form k1 times m plus k2 times n. I think this is Dirichley's theorem. So this is a pretty wide and vast generalization of this theorem that we proved, and it shows that primes come in all shapes and sizes, basically. You can always find infinitely many primes where they're equal to some linear combination of two relatively prime integers. So this is kind of beyond this class, but I definitely gave you a hard problem on the exam, but it's getting you into some real number theory, some real math. So forgive me, I suppose. Okay. Any other questions on that one? Yes? No? Maybe?
I don't have any more questions on that one.
So is it all right if we do some combinatorics problems? Did I give you problem 25? This seems like a fun one.
Well, I have a question about one of the problems from the video.
Okay, sure.
So there was the one about like the sequence proof where it was like it was a sequence of length n squared plus 1, I think. And
Yeah. Right. So every sequence of distinct integers, or distinct real numbers, sorry, of length n squared plus 1 has a either strictly increasing or strictly decreasing sequence of length n plus 1. Is that right?
yeah,
Okay. So this is using the pigeonhole principle. And what's your question?
oh, so you kind of proved that, I think two of the, like you use proof by contradiction to prove that like AI AJ would equal NI NJ or something like that.
That's right. That's right.
And I was kind of confused about how that showed that there had to be one equal to n plus 1.
Right. So the idea, let's work with subsequences of length 5, just so that we can try to do something kind of concrete. So let's say that we have a subsequence of 5 real numbers, and they're all distinct. Then I think I did this kind of explicitly in the video, but if we assume for contradiction that there does not exist a strictly increasing or a strictly decreasing subsequence of length 3, then what I did is I assigned to each number a pair of integers, right? So I assigned a AI and then a DI, where the AI is the length of the longest subsequence, which is strictly increasing, starting with this number. And the DI is the length of the longest strictly decreasing subsequence, starting with this number. So 1 is less than or equal to AI, which is less than or equal to 2, and 1 is less than or equal to DI, which is less than or equal to 2, right? So I can always take a one-term subsequence, which is just taking that number, and one number is always strictly increasing or strictly decreasing. So both of these numbers are greater than or equal to 1, and they're less than or equal to 2 by my assumption, right?
Yeah.
Okay. So what are the only possible options for these tuples?
0, 1.
No zeros, remember?
Or, oh wait, yeah, 1, 2, or 2, 1.
Right. 1, 1. I can always have 1, 1, or 2, 2, or 1, 2, or 2, 1. If I let me just do an example. I think I did this in the video, but I'll do it again. So like 1 pi negative 100, 3, 7. Let me just write out these numbers. So here, I'm looking for an increasing subsequence starting at this number. So if I start here, here are some increasing subsequences. 1 pi 7 is 1. 1, 3, 7 is another one. So here I already have 2. Or I already have a subsequence of length 3. So I would be I'd be done, more or less. I have a long increasing subsequence. So let me make one of these decreasing, like -5, so that I don't have an immediate win. So if I try to write down the longest increasing or decreasing subsequences here, the increasing subsequences are either going to be 1 pi or 1, 3. Everything else is decreasing. So the longest increasing subsequence is length 2. Now, if I want a decreasing subsequence, they're also going to be of length 2 because they're going to be 1, -100, that's decreasing, but then I can't get lower than -100, or 1, -5, but then I can't get any lower. So this is a 2, 2 in here. Is that okay, how I arrived at this pair of integers for this number in this sequence?
Yeah.
Should I do more examples, or is this okay?
No, that's good. But what I was confused about is if you have, so you kind of showed that like you'd have to have a 2, 2, and then maybe later like another 2, 2 or something, or
I'm not
something
saying that it
along
has
the
to be
lines
2,
of that.
2, but if there are
It could be a 1,
5,
2 or something.
right, there are 5 slots and there are 4 possibilities. So one of these 4 has to be repeated twice.
Yeah. So
Right.
what if the one that happened to be repeated twice was the 1, 1?
That's fine.
Then
So
I guess that would show that. Then that would only show that you have 2, 2. But then would you have to use that logic again?
all that you're looking for is a contradiction. Once I have set up this assumption, I'm just looking for a contradiction, right?
Yeah.
So the contradiction that I'm going to get is that I can assign this integer pair to each term. Because if this term is 1, 1 and this term is 1, 1, I get a contradiction because A and B, A is either less than B or greater than B. If A is less than B, then this should be a 2 because there's at least a 2-term increasing sequence that goes A, B. If A is if A is greater than B, then this should be a 2 because I have A comma B being a length 2 strictly decreasing subsequence.
Okay. Yeah.
So I can never have both of these. I can never have 2 1 1s because if I have 2 1 1s, one of them is lying to you because you can always make a longer subsequence because they're all distinct. Either A is less than B or A is greater than B. So it's not possible for there to be 2 1 1 terms. For the same reason, it won't be possible to have any pair. Let's pretend that we had A over here and B over here, such that A is a 2 1 and B is a 2 1. So this is saying, so let's look at the case where A is less than B. If A is less than B and there's a 2-term increasing sequence starting at B, that means I have a BC, where somewhere over here is a C, such that BC is strictly increasing. But then ABC is a strictly increasing sequence of length 3. So this 2 actually has to be a 3. Similarly, if A is greater than B, then here we have a length 1 decreasing sequence starting with B and a length 1 decreasing sequence starting with A, but this 1 must be lying because AB is a strictly decreasing sequence starting with A. So then this has to be a 2.
Okay, so you're basically saying that you can never have 2 tuples that are the same just because that would violate.
Because you can
some other-
always adjoin the first term to either a strictly increasing or strictly decreasing subsequence starting with the other guy. So you can never have 2 of the same pair of integers. Because you can always adjoin A to either a strictly increasing or a strictly decreasing subsequence starting at the other one.
Okay, yeah, thanks.
So the contradiction is that whenever you set up these subsequences, all of these tuples of integers have to be different, but we've finagled it such that if you say that this is not true, then by the pigeonhole principle, 2 of them have to be the same. You can't have both of those things happen simultaneously.
Okay, so yeah, you're basically like forcing one to be greater than 2, so then it would be n plus 1 or greater, basically.
Exactly. You
Okay.
can't have 2 of these tuples being the same, because you can always make a longer increasing or decreasing subsequence by adjoining A onto the corresponding increasing or decreasing subsequence for B.
All right, thanks.
Yep. Any other specific questions?
I guess kind of along that line, there where you proved the pigeonhole principle, you showed that it has to be greater than nk minus 1 or something like that, or like n over k minus 1.
Oh, this was the generalized pigeonhole principle?
Yeah,
Yeah.
but you never showed that it would work for n over k.
You mean if k divides n?
Or no, like you said that it would have to be greater than that to like show that you'd have to do the ceiling of n over k. You showed that like that one of them would have to have like greater than the ceiling of n over k minus 1 thing objects in the hole or whatever.
Yes.
And you showed that it would have to be greater than that, and I'm confused about how that actually implies that you need to have that n over k, the ceiling of n over k would actually work. Because couldn't it be the ceiling of n over k plus 1?
Oh, it's always possible to have more pigeons fitting in the hole, but the only thing that you can get is that you have ceiling of n over k of them appearing. I mean, the terminology in that is a bit kind of confusing, but I believe that I did it correctly. I can check again. But the whole idea is like if you have, let's say 3 pigeonholes, and you have 10 pigeons. Here, the pigeonhole principle ought to say that you must have 4 pigeons in one of the pigeonholes. And 4 pigeons is exactly ceiling of 10 divided by 3.
Yeah, but in your proof, I mean, I don't know if I'm just missing something, but like you said, you basically use proof by contradiction to show that one is going to have more than the ceiling of n over k minus 1. Or the
Right,
ceiling of n over
exactly.
k
So
minus 1.
so if one of them, so the contradiction of one of them having ceiling of n over k, to contradict these many being in one box, I assume that less than or equal to n over k minus 1 are in each box. Right?
Yeah.
And then what I show is that k times n over k minus 1 is smaller than the total number of objects you are given.
Yeah.
So I get a contradiction.
Or yeah, I guess so. I guess yeah, n over k, the ceiling of n over k plus 1 would still fit the category.
So I'm not saying that n over k plus 1 have to appear anywhere, right? For instance, if there are 10 pigeons in 3
Yeah,
holes,
no, no,
I put, there's no n over k plus 1 appearing. There's no, I'm not forced to put 5 inside 1 hole.
yeah, I guess I don't know what I was thinking.
That's okay. The notation makes it tricky, but it's really a kind of a simple sort of thing where, let's say you only had 9 pigeons going into 3 holes, then it'd be possible to put 3 in each, right? You kind of, if k divides n, then put k in each hole. Or, sorry, put n divided by k in each hole. But the point is, the moment that n is 1 bigger than, right, so in this case, n is equal to kd, right? If n is equal to kd plus L for L greater than 0, then immediately I know that if I put D in each hole, I'm still going to have at least L left over. And so 1 more than this is going to have to go in somewhere.
Yeah. Yeah, I get the pigeonhole principle. I just wasn't exactly sure how that showed, but I guess I don't know. I guess just some of the problems that you were going through were kind of confusing, so I was probably
Okay.
thrown off a little bit.
Sorry about that. Right, and the last thing to notice is that n over k plus 1 is equal to ceiling of n over d, or n over k, for n is equal to kd plus L, where 0 is less than or equal to L. Sorry, where L is 1 less than or equal to all the way up to less than k. When I set things up in the divisibility rule, then n over k plus 1 is the same as ceiling of n over k.
Yeah.
Sorry, this is not quite right. This should be D.
Well, it's the same thing.
No, because k doesn't divide n. In this setup, k doesn't divide n, so well, I'm talking about integers here, but n divided by k is a rational number and not an integer.
Okay. Oh wait, oh, you're talking about the d kd plus L, not d. Above you wrote d equals n over k.
Yeah, this is all the same. N is equal to kd is the same thing as d is equal to n over k. In this case, okay. I'm being a little sloppy here. So really what I'm talking about is this case. When n is equal to kd plus L, where L is some remainder, then d plus 1 is the ceiling of n over k.
Yeah. Yeah, I get what you're trying to say, but
Sorry about that. Yeah, the notation gets a little hairy.
okay, yeah, thanks.
Sure. Lucia, I don't know if we've taken up all of the time and didn't get to do any more exercises on the combinatoric side.
Can you?
Yeah.
Can you just like review the seating for out of 10? Because I noticed that you said that you needed to divide by 4, but I didn't really get that part.
You mean for this?
No, it was like a different example from 6.1.
Okay.
It was,
Oh,
how
the
many
seating.
ways- Yeah, how many ways of seating?
Right. Okay. So for these combinatorics problems, it's sometimes good to draw a bunch of things out. So we've got 10 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the point is, let me make a table which looks like this. One person's going here, one person's going here, one person's going here, and one person's going here, right? Now the point is, the number 10 times 9 times 8 times 7 is the same as an ordered choice of 4 people from this set, right?
Okay.
Namely, first I pick, say, person number 6, and then I pick person number 2, and then I pick person number 1, and then I pick person number 10, right? But the point is that this number is counting the ordered selections.
Okay.
And if they're already in order, then I have to remember that order when I put them on the table. So if I line them up like this, 6, 2, 1, 10, then that I should think of that as if I start my table here, I put the first person here, I put the second person here, I put the third person here, I put the fourth person here, right?
Mm-hmm.
Now the point is, think about this table. 6, 2, 1, 10. This table corresponds to choosing first the person 10, then choosing the person 6, then choosing the person 2, then choosing the person 1, right?
Yeah.
So these are 2 different permutations, that is 2 different elements inside a set of this size, but we want to treat them as the same because I said that these 2 different seating arrangements are the same because 6 has 2 to their left and 10 to their right, and 1 has 10 to their left and 2 to their right. Right? So these 2 seating arrangements are the same.
Okay.
And in fact, there are 2 more seating arrangements which are the same. Also this arrangement where I have 6 down here, and I have 2 over here, and I have 1 up here, and I have 10 over here, which it corresponds to 1, 10, 6, 2. This is also the same table according to how we're treating tables, and the last one is going to be 2 on top, and then 1, and then 10, and then 6. And this corresponds to the ordered choice 2, then 1, then 10, then 6. Right?
Uh-huh.
So this number, 10 times 9 times 8 times 7, is treating all of these as different. This is one element in a set of this size. This is another element in a set of this size. This is another element in a set of this size. And this is a 4th element in a set of this size. But all of these I'm going to count as just one seating arrangement.
Okay.
Because
So
they
you
all
you
correspond to the
divide
same
it.
table.
Okay, so
Because
you divide it because it's technically the same. It's just
exactly,
one
I'm
order.
deciding that these are the same. So every sequence in a set of this size, which is a choice of 4 people, I'm going to say this sequence is the same as rotating this sequence. You see, I'm kind of, it's easy to see with a table that I'm just rotating the table, and then you see what are the sequences that I'm saying are the same in this set. And since I can do this with every sequence in here, then I'm dividing this whole number by 4.
Okay, I think that makes sense. All right, yeah, thank you.
Yeah, sure. All right, that is a full hour and 15 minutes for office hours, and I think that'll be about it for me today. And yeah, I'm working hard to finish up giving your grades back. Almost all the tests have been graded. I will record the last lecture for Thursday right after this class, and then I'll start writing the final. A lot of work. I'm sure you all have tons of work as well, of course. So, any last questions?
there be will there be any review sessions after Thursday?
I wasn't planning on it now,
Okay.
but I encourage you to reach out to other people in this class and ask questions about stuff.
Okay. Thanks.
All right. Have a nice afternoon, everyone.
Yeah, you too.
Have a good day.
So long.